All right, so we're going to start our chapter on organic chemistry, topic 10, with learning how to name organic molecules. This is something that is really important for all facets of chemistry because we're often dealing with organic molecules in stoichiometry and acids and bases and in any of the other aspects that we've covered in chemistry. So understanding the nomenclature behind them is incredibly important. But before we start, we're going to just look at how to write a couple of different formulas. So we're actually in, if you're following along with our textbook, we're actually in section 10.1.2, which is the molecular and structural formula section. Okay, so organic compounds can be represented in a few different ways. The first, which we've come across before, is the empirical formula, which you can probably remember is the simplest whole number ratio of atoms in a molecule. The second way to represent them is their molecular formula. Whoops. So that's the actual number of atoms that they contain. And finally, we have the structural formula. This is the structural formula is what we're going to use a lot to learn how to name them. So for the structural formula also, we'll break it down in a second, but it can be broken into the full structural formula. So this down here is a breakup of the structural formula. So it can be broken into the full, the condensed, or the skeletal. Okay, so all of these are different ways to write the structural formula. So let's take, for example, ethane. So ethane is our molecule C2H6. So the molecular formula for ethane would be just that, C2H6. The empirical formula, the simplest whole number ratio, would be CH3. And the structural formula, so we have three different options here. The full structural formula, we actually draw out every atom and every single bond to each of those atoms. So carbon, two carbons attached, and our hydrogens. We have the condensed, where essentially the condensed, we write all of the carbons in order, and all of the bonds attached come after that carbon. So CH3, CH3 would be our condensed form for that. And our skeletal, forgot a T here, in this case, we represent, for our skeletal, we represent the molecule as a simple line. Okay, so it's a little strange to get used to skeletal structures at the beginning. Okay, so all atoms except carbon atoms are omitted, and carbon atoms are represented by the intersection or ends of a line. So that's ethane. Let's take propane as another example. So propane is 3 carbons and 8 hydrogens. So for propane, the molecular formula would be C3H8. The empirical formula is still C3H8. It does not change at all. The structural formula, we have three versions. We can have our full structural formula where we write out each carbon, each hydrogen, takes a long time to do this one, which is why we don't normally use it, are condensed. And the easiest of them all, the skeletal. So the important thing to remember with the skeletal structure is that each intersection of two lines, or the end of a line, represents a carbon. Carbons always have 4 bonds. Okay, so since carbons always have 4 bonds, however many lines are not there, that's how many hydrogens are on the carbon atom. Okay, so for example, this carbon here would have 3 hydrogens coming off of it because it currently only has 1 line or 1 bond to another atom shown. Anything other than carbon, such as oxygens or halogens like chlorine, fluorine, iodine, bromine, anything else will be drawn on and actually shown out. And we'll see this as we come and study functional groups later on, as well as double and triple bonds will also be fully drawn out. Okay, so this is just a quick overview of the different types of ways we can draw organic compounds or write them out. Okay, so now we're going to jump into the naming of organic compounds. So for naming, and again, if you want the book section, this is section 10.1.5. So for naming chemical compounds, the people who derive this, the organization in the world, is IUPAC. IUPAC. This stands for the International Union of Pure and Applied Chemistry. Okay, so this group of people, this International Union of Pure and Applied Chemistry, came up with a naming system in order to name everything, not just organic compounds, but they're the ones who decide the name for essentially all chemical compounds. Okay, but for organic compounds specifically, organic compounds consist, the names consist of 3 parts. There's a root. Okay, so the root word, which depends on the longest carbon chain in the molecule. I should say the longest continuous carbon chain. Okay, so there's the root, there's the suffix. Okay, and the suffix differs according to the functional group present. Oh, need another C in there. According to the functional group. So that's something, a functional group is something other than just a simple carbon-carbon bond. So an oxygen can be an oxygen in a compound means it has a functional group. A double bond is a functional group. A nitrogen or a halogen are considered different functional groups, all having different ways to name them. And then lastly, there's the prefix. So what comes at the beginning of the word identifies the position of any substituent groups. So that's any branching groups, and you'll see what I mean by branching groups in a little while. Now, this root word, okay, when we name the root word that's based off how many carbons are in the longest chain, we have to know how to name that. So the number of carbons in a chain okay, for your purposes, generally we only see carbons up to a maximum of 6 for the longest. But based on those 6, you can see up to 10 occasionally, but the IB expects you to be able to name things with up to 6 carbons. The stem word, or the beginning word that we start everything with, 1 is meth, 2 is eth, 3 is prop, 4 is bute, 5 is pent, 6 is hex. Okay, and then the suffix would come after that depending on the functional group present or lack of functional group, and the prefix comes beforehand, which tells you about what else is attached to this main chain. If you do happen to come across additional carbons, 7, 8, 9, or 10, okay, 7 we use hept, 8 is oct, 9 is known, and 10 is deck. So there is a chance you could see them, but again, IB says you only need to know how to name 1, 2, 6. So we're going to start this naming with straight chain alkanes. So an alkane is a carbon compound that contains just carbon and hydrogen. It does not contain any additional types of atoms, just carbon and hydrogen. It does not contain any double bonds. So these are the simplest type of organic compounds to name. And it's based by starting off with figuring out the number of carbons in the main chain. Okay, the root word, like we saw before, or the stem, the root word can change depending on the number of carbons. The suffix for an alkane is ane. Okay, so the suffix for any alkane compounds is ane. So for example, let's draw the first few. So we could have methane, which means we have our root word is meth, meaning 1. Our suffix is ane, meaning that it just contains carbon and hydrogen. So we have 1 carbon, and we need 4 bonds to that carbon. So we draw methane, or the condensed structural formula CH4. Ethane would be 2 carbons. And again, we know eth means 2. That's our root. Ane means it's an alkane. So our condensed form CH3, CH3. We'll do a couple more. Let's do propane. I'm going to draw the skeletal form here, though, and then the condensed down below, just to save some time. If you want to draw out the full structural formulas, feel free to do so. We can have butane, meaning 4 carbons. So we have our starting carbon 1, 2, 3, 4. So 1, 2, 3, 4 carbons. And again, our condensed is our CH3, CH2, CH2, CH3. So this is the simplest type of naming that there is. And you have to know up to hexane. When we have groups like this in a series, so all part of the alkanes and all differ by just adding another carbon with its hydrogens, we call, moving up this series, we call this group a homologous series. We're going to get to a lot more on homologous series later, but an alkane, so this grouping of alkanes, methane, ethane, propane, butane, is an example of a homologous series. And their chemical and physical properties change predictably as you move up the chain. So the next thing we're going to do is we're going to look at branched chain alkanes. So again, we're just starting with alkanes. We're not adding in any functional groups yet. This is the only thing. So this gets a little more complicated though, and it's important that you understand branched chain alkanes as best as you can, because these properties, these principles will apply once we start adding functional groups as well, and things can get fairly complicated with the naming at that point. So to name branched chain alkanes, there's a couple of steps. Step 1, okay, identify the longest continuous carbon chain. That's going to form the basis of our name. So that's going to be our root word that we use, whether it's F, Pro, But, Hex, any of those. 2 is identify the side chains, or what we also call substituent groups. Okay, identify side chains and name them. So we use the same table from the root word, so our meth, eth, pro, but, pent, hex, to name our substituent groups as well. If there's more than one of the same substituent group, then we have to use our prefixes di, tri, tetra, and so on to say how many there are. So again, that word would be put in front, so of the meth. So this would be a prefix that we would put on, stating the number of that particular type of branching group. Okay, so lastly, so we identified the side chains and the type of side chains. Lastly, identify the position of the side chains. So identify side chain position. And what we do is we number the carbon atoms of the main chain, and we want the side chain position on the lowest number carbons possible. So if you are naming a group, and there's a different way to number the main chain that puts your numbers so they're lower, that is the option you want to use. Okay, when you're naming side chains, you change the ending of the root words. So the name for side chain names, we change the suffix on them to a YL. Okay, so for example, if you have a side chain that is 1 carbon big, so a meth, we would call it methyl. If you had 2 of them in your compound, it would be a dimethyl. Eth would be ethyl, prop would be propyl, but would be butyl, so on and so on. So let's try naming a couple of these. I'm going to draw a branch chain alkane, and I want you guys to attempt to name it. So you can just pause the video after I have the structure drawn here. Take a minute, see if you can figure out the name, and then we'll go through it together. 3. Oh, I should probably keep my formatting the same here. So CH. There we go. So there's the first one. And the second one I'm going to draw the skeletal structure for. Try to name this one. So here's our skeletal structure. So again, pause the video, take a minute to try to name each of those, and then we will go through it together. Okay, so let's start here with the first one. So the first thing we want to do is number our longest carbon chain, or find our longest carbon chain. So I'm just going to start to the left. I'm going to number this carbon 1, 2, 3. Now I have a choice. There's a branch. I'm going to keep going left or right because there's 2 carbons here. So 4, 5. So our longest carbon chain here is pent. And if we look, there's no sign of anything other than carbons and hydrogens. So we know that our suffix, our root word is pent, and we know that our suffix is going to be ane for pentane. Okay, then what we want to do is look for any branching groups. So we have one branching group here, and we have one branching group here. Each group consists only of one carbon, so they're both meth groups, but we have two of them. So we have to name it dimethyl. Remember, this is all one word. But now we can't just say dimethyl, we know there's two, but how do we distinguish it? We need to say the positions they're on. So we have one on carbon 2, and we have one on carbon 3. So the name of this compound would be 2,3-dimethyl pentane. Okay, so 2,3-dimethyl pentane. Then double check, is there a way you could number this differently in order to put the carbons at a lower number? So for example, if we numbered it backwards, 1, 2, 3, 4, 5. In this case, if we named this compound with the orange going backwards, it would give us the compound, it's still pentane, it's still dimethyl, but it would give us 3,4-dimethyl. Since 3,4 is higher than 2,3, we stick with our initial 2,3 naming. Let's move on to the second one. So here, first we have to again count our number of carbons. So our carbons are at the end of a line or the intersection of two lines. So we can start here, or we can start at the lower carbon here. It doesn't actually matter. Both consist of 2 before hitting the chain. So I'm going to start at this one, call this carbon 1, 2, 3, 4, 5, 6. So we have our root word, which is hex. Okay, and our suffix here, again, it's just carbons and hydrogens, is going to be ane. And then we go back, we figure out, okay, what do we have for branching groups this time? We have one branching group here, and we have one branching group here. Now this one at the top only consists of one carbon, so we'd have a methyl. This one at the bottom is 2 carbons big, so one carbon here, one here, so it would be an ethyl. Okay, so how are we going to name this? Well, we need the numbering position. This does seem like the lowest number. Yep. The lowest possible numbering scheme that we have. Interesting. If we flip it around, it would still be on 3 and 4. So that's a good question. How do we know which way? We'll talk about that in a second. But for now, let's write them down. So we always write the word in the prefixes in alphabetical order. So since E comes before M, we write ethyl first. So we're going to have 3-ethyl, 4-methyl hexane. And that will be the name of our compound. The ethyl group in this case we will leave on 3, again because it's first in the naming. Ethyl will take priority, so we'll put that on the lowest number carbon over the methyl group on 4. Okay, so that's 2 examples of branched chain alkanes. Okay, so let's move on to our next functional group. Okay, next we have the alkenes, the alkene family. Okay, the alkene is when we have a carbon double bond present in our molecule, and the suffix for an alkene is, of course, ene. Okay, so again, this is when we have a carbon-carbon double bond. So we can't can't have methene because there's only one carbon. But we can have, for example, ethene, ethene. That is when we have carbon attached to a carbon, so only two carbons for our eth. Ene says there's a double bond. Now each carbon needs 4 bonds, so the other 2 would be hydrogens. We can have ethene, we can have propene, C, double bond C, a single bond. Oh, only have 1 there. We don't want to have 5 bonds to a carbon. And here we would have 2. So if we were to write these as our condensed form, this one would just be CH2, CH2. Our propene would be CH2, CH, CH3. So just write them as they come. Butene. Again, I'm going to use 2. So now we have a problem. Because we can put a double bond here. This is how we draw a double bond in a skeletal structure. So we just add a second bond to the first. Or we can put a double bond here. So the difference is the location of the double bonds. So here, if we number the carbons, the double bond starts on carbon 1. In the second image, it starts on carbon 4. So we actually have to change the name to represent where the double bond is starting. So this one would be but1ene. So again, it's coming the number's coming before the suffix now because it's talking about the suffix, whereas this one would be but2ene. So the position of the double bond does in fact take into consideration. We do have to take that into consideration with the number. And a very important fact here is that even if we have other functional groups or other branches in our compound, the double bond will always be on the lowest numbered carbon. Okay, we always try to put it on the lowest number as possible, just like we do with the branched chains. So let's try this with a branched chain. I'm going to do a skeletal structure again here just to keep it easy. So we'll try an example. There we go. So try for a second. Again, pause, give yourself a chance. Try this to name this structure. Okay, so first thing we do is we need to count our longest carbon chain. Now the double bond has to be a part of our longest chain. Even if it's not the longest chain, we still make the double bond a part of it to do our naming for what the IB expects you to need to name. So we're going to start here, 2, 3. Now we can branch to either side. Okay, both are 2 carbons long. So I'm just going to go 4 and 5. Okay, so our root word here is pent for 5, but we have a double bond on carbon 1, so it's pent1ene. Now we also have a branching group present. Okay, that's 2 carbons long, coming off of carbon 3 of the main chain. So 2 carbons is an ethyl. So we're going to call this 3-ethyl pent1ene will be the name of this compound. Again, the hydrogens are not shown on the compound here. Now you may ask yourself, what does the condensed form of this compound look like? So if we wanted to do the condensed form, we have to start with carbon 1. Okay, so imagine we're starting here. Since this carbon has 2 bonds, there would be 2 hydrogens. Okay, let me just quickly draw on some hydrogens here. There'd be 1 hydrogen here, 2 here, 3 here, 2 here, and 3 here. So we start with carbon 1, CH2. Then we move to carbon 2, which is just a CH. Then we move to carbon 3, which is another CH. Okay, and then we have a problem because we have a branching group. So to represent the branching group, we're going to put in brackets CH2, CH3, because that's what comes in our branching group. And then we continue the chain along the other side for carbon 4 and 5. Carbon 4 is CH2, and carbon 5 is CH3. So you can see how these condensed structures can get a little bit complicated. It will take some time to get used to writing them out and reading them as well. Okay, so the next functional group that we have to name is the alkyne. The alkyne, our suffix is YNE, and an alkyne represents a triple bond between two carbons. Not incredibly common to see alkynes. Might have to name a couple of them here and there. So let's take a look again at a few. We can't have methyne. We can have ethyne, which would be carbon triple bonded to a carbon and then a hydrogen on either side. We could have propyne. Now, when a carbon is triple bonded, it will always make a linear bond. Okay, and then another carbon, H. So again, our condensed forms for these, this would be CHCH. This one would be CHC, CH3 due to that triple bond. And then our bute, again, we can have two different positions. We can have bute 1-ine or bute 2-ine, where we would have a triple bond. Oh, I shouldn't draw it so it is linear. So we would have a triple bond on carbon 1 and then another carbon coming off here. So 1, 2, 3, 4. Or we could have a triple bond on the middle carbon to make bute 2-ine. Okay, we won't go over any specific examples for this because it follows the same patterns as the ones that you saw before. Oh, and the condensed structures for these would be CH, C, CH2, CH3. This one would be CH3, C, C, CH3. You notice that the molecular formula for both of these is C4H6, and this one is also C4H6. So the structural and the condensed forms let us distinguish between the two different versions of butene, bute 1-ine and bute 2-ine, but the molecular formula does not. It doesn't tell us anything, it just tells us the pure number of carbons and hydrogens. All right, so the next group, we have alcohols. So the alcohols have the suffix, you can probably guess by now, al, OL. Now, we'll take a look in a second what happens. The suffix for alcohols being a functional group actually has to combine with one of the previous three suffixes we saw as well. So depending if you have all single bonds, then you would have ANOL is for alkenes. If you have double bonds, you would have ENOL. And triple bonds with alcohols would be YNOL. So you can have three different endings. This goes for all the functional groups based on the number of carbon bonds that there are. Okay, but again, it follows the exact same rules as we did previously. So we can have, for example, methanol, which would be OH. So the OH is the alcohol functional group. So if you see an OH somewhere on a compound, that means you have methanol. We could have ethanol. So once you start getting to larger groups, again, you'll have to start labeling where the alcohol is located. For example, we can have propan-1-ol, in which case we have our 3 carbons, so propane, and the alcohol is on carbon 1. Or we can have propan-2-ol, in which case we have our 3 carbons and the alcohol is on carbon 2. We could also have, for example, if we doubled the number of alcohols, we could have ethanediol. Now we need to distinguish again, because does ethanediol mean we have an alcohol on carbon 1 and an alcohol on carbon 2? Or does ethanediol mean we have 2 alcohols on carbon 1 and none on carbon 2? Okay, in these cases, we do have the top one is ethan 1,2-diol, and the bottom one is ethan, in this case, 1,1-diol. You do have to say 1,1 because if there's 2, you have to say the position of both, even if they are on the same carbon. So let's take another chance here to do an example. So I'm going to draw a molecule out here. How about this molecule? So again, try a second to name this. Okay, so if we start by, oh, you know what? Actually, let's make it a little, no, we'll keep it like this. So if we start by labeling our longest carbon chain, oh shoot, no, hold on. Erase this for a second. I forgot a couple of carbons. Let's go back. The name of that one would have been butane 2,3-diol, though, of that previous one. Let's do a harder one. Butane 2,3-diol. Let's do there. This is what I meant to make before. Here we go. Let's try this one. A little bit harder. Okay, so the first thing we do, label our longest carbon chain. Now we want our functional groups present in the carbon chain. So 1, 2, 3, 4. Okay, so we have an OH on 1, we have an OH on 4, and we have a double bond between 2 and 3. So 4 carbons, our root word here is going to be bute. It's going to be bute 2 En, because there's a double bond on 2, 1, 4, diol, because there's 2 alcohols on carbon 1 and carbon 4. So this is the suffix 2N14-diol. We also happen to have some functional groups on here. We have a methyl here on carbon 2 and a methyl here on carbon 3. So we're going to have a dimethyl. So it's going to be a 2,3 dimethyl bute 2N14-diol. So this is where names can start getting fairly complicated, which is why a lot of practice is very important when trying to name organic compounds. Next, another functional group containing oxygen. So we looked, our first one was an alcohol that contains oxygen. Our next one we'll look at is a carboxylic acid. So carboxylic acids contain the ending COOH on a molecule. So that's what we look for when we look for the functional group. And it has the suffix oic acid. So for example, methanoic acid is a carbon, so we need to see that OOH functional group, which looks like this. So OOH, and then there would just be a hydrogen on that carbon. We can have ethanoic acid or acetic acid, which would be CH3COOH, and so on, propanoic, butanoic, with that COOH on the end. Now, because the COOH, the carboxylic acid group, is on the end of the carbon, we don't need to label it. It's always going to be on carbon 1, unless the case is where there's more than one functional group or more than or branching groups, then we have to put the number on the carboxylic acid. Okay, so it follows the same as alcohol, but you'll always see the COOH on the end. So methanol looks like, methanoic acid. Wait, where was I again? Ethanoic acid. We have CH3COOH. Methanoic acid, we have HCOOH. A little bit different than before. And so on with the other ones. Now we can also have examples for, we can have propandioic acid. Now propandioic acid, because the carboxylic acids have to be on the end of the chain, we have to start with one, CH3COOH, C. Let me do this in the proper orientation here. CH, H, and COOH. So if we see a dioic acid, it just means that we have two carboxylic acid functional groups present in the compound. Okay, so that's another one containing a alcohol group. Okay, the next one we can have, let's do aldehydes first. So aldehydes are when we have the ending CHO. Again, aldehydes appear at the end of chains, and we give them the suffix Al if you have an aldehyde. So similar to carboxylic acids, but only one double bond O at the end of a chain. For example, methanal is C double bond O with a hydrogen on either side. Ethanal, we have our initial carbon, then we have our carbon with double bond O, and make sure if there's a hydrogen there with a double bond O, it's an aldehyde. If this is an OH, then we have our carboxylic acid again. When we write our condensed form for this one is HCHO. Here we have CH3CHO, so that's CHO. You can recognize if you see that in a compound, generally that is indicative of a aldehyde. And again, you can have dials as well. You can have ones with two carbons. So that is aldehydes. We're also going to look, because this is a similar one, at ketones. Now, ketones are a C double bond O group, but in the middle of a chain, not on the end. The suffix for a ketone is ONE. Now we can't have methanone because there is no middle of a chain. We can't have ethanone. So the smallest ketone starts at propanone. Okay, and again, propanone is when we have a carbon, H3, NaCH3. So it's when you have a C double bond O in the middle of a chain. You can have butanone, which is 4 carbons and a double bond O in the middle. It doesn't matter where it is. It's on. We would label it carbon 2 regardless of the position. We can have propan-2-one, or just move this propan. Whoops. 3-one. Okay, again, 5 carbons. Propan-2-one. It's on carbon 2, depending on which side you number from. Propan-3-one. It's on carbon 3. So these are our aldehydes and our ketones, which are other two groups containing oxygens. There's 2 oxygen-containing groups left. So we have ethers is our next group we're going to look at. Now ethers, when we have an oxygen that conjoins 2 separate carbon chains. Okay, we're going to talk about properties of functional groups later on, but ethers are generally very volatile groups. These other groups we were looking at, so carboxylic acids, for example, have hydrogen bonding. Ethers do not, so they don't have an oxygen bonded directly to a hydrogen. It gives them a very, very, very potent smell. So when we name ethers, okay, these ones are a little bit different. And there's actually a couple of different ways to name ethers. So we use the word oxy, O-X-Y, when naming an ether. And this oxy depends on where or what is on either side of the oxygen. So, for example, we can have methoxy methane. Okay, what this means is this first word, methoxy, means there's a methyl group on one side of the oxygen, and then our main chain, methane, means there's a methyl group on the other. So this would look like CH3. These ones can be a little strange to name. O. CH3. So that would be methoxy methane. We could have, for example, we could have methoxy ethane. Now, why is ethane my root word? It's because Eth2 is my longest carbon chain. So this would be CH3O, CH2, CH3. Now this is where the naming can get a little confusing for this, because for example, I'm going to draw these first. We could have a methyl group attached to an oxygen, and then attached to a propyl group, so CH2, CH2, CH3, 3 carbons. But we could also have this same compound with a methyl group and then attached to the middle of a propyl group. Okay, so in this case, this piece, because it is our prefix, the methoxy is our prefix, so this piece is our functional group. So we say where that's located. So this one would be 1-methoxy propane, and this one would be 2-methoxy propane. Okay, so again, ethers can get a little peculiar, but it still follows the same set of rules. All right, so the final oxygen-containing functional group that we need to look at naming are esters. Oops. So esters are a little bit different. Esters are when we have a chain of carbons, which we represent with an R. So R represents any generic chain of carbons attached to a carbon, which is attached to what looks like a carboxylic acid, except instead of a hydrogen here, this is attached to another different chain of carbons, which I can distinguish it between by using the R prime. Okay, so when we name these ones, we give this the ending word -08. So the suffix is -08. So how we do this in terms of priority is the chain. So this piece that's attached directly to the double bonded carbon, that is our main chain regardless of the size. This one is considered our branching chain. Okay, this one is what we derive our root word for. So this again is an ester. So for example, if I was to draw the compound CH3, COOCH3. Okay, here we have an ester because we have what looks like a carboxylic acid but attached to carbon chains on either side. We look at the group attached directly to the double bonded oxygen, which is here. Okay, it's 2 carbons long, so we give it the name FN, because there's no double bonds, so it's AN, ethanoate. Here on our other side we have a methyl, so we call this methyl ethanoate. No space between here, by the way. We keep everything, if it's letters, we keep it as one word, except the acid at the end is the only time we have 2 words. So let's take another one just for fun. Let's say we have, I'm going to do it as a skeletal structure, so we can practice doing those ones. Let's say we have this compound. Okay, so we start by looking at the carbon attached directly to our double bond oxygen. So here we have 3. And on this side, in our functional group, we have 2. So our functional group is ethyl. And our main group here is propene. So we have a double bond. So we're going to have ethyl. And now we have to add a couple of numbers in. So prop, our double bond is on carbon 1, En, 3, O8. So I'm going to always label where each group is if there are multiple numbering schemes that we could number it by. Okay, so this is an ester, and this is the end of our oxygen containing groups. So we just have 3 more groups left to look at. So we have our next group, just change back to my red here, is the halogenoalkanes. This is when you have, for example, a chlorine. Let me go in order. When you have a fluorine, chlorine, bromine, or iodine attached to one of your carbon chains. So when we have these we call them halogenoalkanes. When these are attached to a group, we call them a halide, which stands for salt. So a halide functional group. We give them the names, so these would come as a prefix to your group, but we give them the names. F would be fluoro, C would be chloro, B is bromo, and I is iodo. Okay, so those are our words that we have. So for example, we could have dichloromethane, which is a regular methane, but with two chlorine groups instead of hydrogens. Okay, we could have let's make this 2,1,2-dibromoethane. Okay, which would be an ethane, so CC, but we have a bromine on carbon 1, and we have a bromine on carbon 2. So just like naming, almost like our alcohol groups or those other things, we just have to name the position and then add the word in front of our word this time. So halogens come as prefixes, not as suffixes like most of our other functional groups. So we're going to stop here with the naming for right now. We'll do nitrogen containing compounds and aromatic compounds in the next video. So for now, here's the basic tools you need. Go through that worksheet that you have on organic nomenclature. Skip the ones with nitrogen currently and try to name as many of those compounds as you can. Okay, if you run into something that we haven't covered, just skip it for now, and we'll get back to it when we learn how to name the rest.